So today we're going to talk about a really important concept, and that's this, that changing magnetic fields cause a current. So a strong magnetic field won't cause a current, and a weak one won't. The magnetic field has to be changing. And today we're going to talk about the general form, a general principle, and we're going to do equations in our next video. So the general idea is when there is a change in magnetic flux, and remember that was the number of field lines, current flows. To resist the change. Okay, so we have to have a change, and then current's going to flow to resist it. So if the magnetic flux, the number of lines, is decreasing, current is going to flow to increase the number of field lines to resist that change. And it may not make a whole lot of sense till we do a couple of examples. So our first example is going to look like this. We're going to have a loop, and we're going to have magnetic field lines or magnetic flux pointing into the page. And then we're going to slowly increase the magnetic field. All right. So I actually write this out. It's a three-step process. If you start to understand it, you don't have to write out each step, but the first few times at least it's going to help probably. All right, so we have to identify the change. Well, it's increasing, and the X is mean into the page. So we have increasing flux inward. Now to resist that. All right. Well, there's two things that are opposite of increase in. We don't want to say decrease out. That's a double negative. We're changing both of them. We could decrease the in. Okay. Increase in is the opposite. Sorry, decrease in is the opposite of increase in. Or we could increase the flux going out. And we're always going to choose the increase version. Okay, these are both really the same thing. We're going to choose to say it as increase out. So maybe make a note over here. We choose the increase version. So we're going to choose the one that's increasing. The reason why is that direction is going to be important. Because when we want to know the direction of our current, we're going to use the third right-hand rule where our thumb is the magnetic field and our fingers are the current. And this tells me which way to point my thumb. So my thumb has to point out, and then my fingers are going to curl in the direction of the current. So my thumb comes out of the page. Oh, look at that, my fingers are curling counterclockwise. So the current will be counterclockwise. Okay, so what it's saying is this is increasing inward. To combat that, I have to increase out. If the current flows counterclockwise, it gives me an outward field to balance that inward field that's increasing. Now, the next example is going to be a really important example, like in terms of real life. All right, I'm going to start out kind of with the same picture. I have a bunch of inward flux lines here. And what we're going to do is flip the coil 90 degrees. So right now, all 9 of those lines, if I think of those as 9 field lines, are going through the center of the loop. If I flip the loop 90 degrees, okay, so here's my loop, and all 9 lines are going through it. If I flip it 90 degrees, now none of the lines are actually going through the loop. They're going parallel to the loop. So this drops the flux to 0. So our change in that case, so I'm dropping it to 0, that's decrease. And the X's are telling me that the flux is in. Now, the reason this is important in real life is we generate almost all of the electrical power we use all around the world using this idea. Because if I continue to flip it, I flip it 90 degrees, the flux goes to 0. Then I let it continue to flip another 90 degrees. Oh, now the flux is all going through it again. And then another 90 degrees, none of it. So as this coil spins, all right, the amount of flux is continuously changing, so I'm continuously producing current. And here in Rochester, we get most of our power from the Gannett nuclear power plant. At Gannett nuclear power plant, you take the nuclear power, heat up water, make steam. The steam gets forced through a turbine, which is like a big fan, and that spins, and it spins a coil. At Niagara Falls, the water rushing through a turbine causes the turbine to spin, spins a coil, continuously changing field. Coal power works the same way. Use the coal to heat up water, to make steam, to spin a turbine. And in wind power, it's obvious that the wind is spinning the windmill blades. The windmill blades are spinning a coil, and as it spins the coil, the flux is continuously changing. Now, back to this example. Change is decrease in. To resist that change, we have to do the opposite. So I can increase in. That's the opposite of decreasing in, or decrease out. Decrease out. That's the opposite. Okay, I change either of those two words. So increase in is the opposite of decrease in, and decrease out is the opposite of decrease in. And remember, we always choose the increase. And then after in is telling me which way to point my thumb. So then the current is going to be, my thumb goes into the page, and my fingers curl around clockwise. Okay, so the important things to remember is there has to be a change in flux. The current flows to resist that change. All right, and you're going to have to figure out the direction that the current flows in order to resist that change. And one really kind of important real life application of this is almost all of our electrical power is generated this way.